and welcome to another video. In this module, we're looking at the very first one in Year 12 Advanced, which is going to be sequences and series. So before we get into applying all the different formulas that there are in this topic, I just want to really break down what this topic is all about. So when we refer to sequences, it just means that we have a list of numbers that follow some sort of pattern. So I've written down 3 over here. The first one, it goes 5, 10, 15, 20. If I ask you to continue the next few terms, you would say 25, 30, 35. And you would notice that the pattern going on here is that you keep adding 5 every time. So we add 5, add 5, add 5. When the sequence differs by a common value where you're adding or subtracting the same amount every single time, in this case, we're adding 5 every time, we call this type of sequence an arithmetic or arithmetic sequence. We can also shorthand it and call it an arithmetic progression or an AP. So I'm going to be throwing AP a lot because it kind of like flows out the tongue easily for me. Now, the next one, if you look, we have 4, 8, 16, 32. Now, do you notice what is the pattern here? If I ask you to find out the next number, you'd say, oh, 64, and then 128, etc. So in that case, every time we go from one term to the next, we're timesing by 2. So when you're timesing by a constant amount every time, we call that value that we're timesing by a common ratio. And we say that the type of sequence that this is a geometric sequence or a geometric progression or a GP. Now, when you have a sequence that looks like this, 1, 4, 9, 16, to continue it on, it's going to be 25, then 36, then 49, etc. Now, if I ask you, is this an AP or a GP, does it differ by a common value? Okay, you can see you add 3, then you add 5, and then you add 7. That's not really going to work. And then if you times it times 4, that doesn't times by 4, so it doesn't work. So it's neither arithmetic nor geometric, therefore it's neither. Now, there's nothing wrong with this type of sequence. It's still a sequence because there's a pattern going on, but in Year 12, we only focus on APs and GPs strictly, and we get really good at dealing with those type of sequences. Now, that's what the first part of this topic is about. Next, series. When I refer to series, it's very simple. It's just the sum of the terms in the sequence. So if I look at this first sequence here, if I wanted to add the terms in that sequence, then I'd just be 5 plus 10 plus 15 plus 20. And then the same thing, you add these terms of the sequence. Now the notation we use for series is a big S, and we usually put a little subscript, like a mini number at the bottom, which refers to how many terms you're adding up. So if I look at my first sequence, this one over here, if I wanted to add the 5 terms in the sequence, then I'm going to write S5, where I'm adding up the first 5 terms. This is going to be equal to 5 plus 10 plus 15 plus 20 plus 25. And then you can pop it in your calculator for small values like this. But then later on, we're going to be looking at a formula that can help us quickly calculate it, because we might have, let's say, 50 terms, or we might have 1,000,000 terms. So we don't want to have to be continuously adding it every single time. So for the very first video of this module, we're going to be focusing on arithmetic sequences or arithmetic progressions or APs. I'm just going to call it AP just to be very straightforward. So let's just study it by looking at these 2 examples here. So in the first example, we have this very simple AP. We have 3, 6, 9, 10, 12. Hopefully you'll be able to recognize that they all differ by adding 1 every time. So the notation we use to refer to how much they differ by is going to be lowercase d, and it's going to be positive 3 because we're adding 3 every time. Another notation we use is a is equal to 3. Another notation we use is a is equal to 3, where a represents the first term. Kind of like in the alphabet, a is the first letter, a is the first term of the sequence. Now, another thing that we should keep in mind is that when we look at each terms in a sequence, we also denote them by this other notation where it's t and then some sort of number. So the first term is called t1 because t stands for term, and then the number stands for which number that corresponds to. And t1 is equal to 3. t2 is equal to 6, or the second term is 6. And if you look at the last one, the 5th term is 12. So you have to kind of wrap your head around the fact that every single term so the term is the actual number in the sequence, is going to correspond to a number, and the number always starts with 1. So that's n is equal to 1, that's n is equal to 2, that's n is equal to 3, dot, dot, dot. This is n is equal to 5. Okay, now if we look at this sequence over here, we can see that it goes 7, 4, 1, -2, -5. So the numbers are going smaller, and they're going smaller by 3 every time. So when you're decreasing in the terms in your sequence, we're going to be minusing. So the common difference is a negative. And then A, your first term is 7. Once again, we have to be familiar with the notation of T1, T2, etc. The very first formula we're going to be exploring is the formula that we use to define an arithmetic sequence. So we can say that the sequence is an AP if this is true. If T2 minus T1 equals to T3 minus T2, or in other words, if the difference between the second and the first term is equal to the difference between the third term and the second term, then therefore this is going to be an AP. Now you might be thinking, like, why is that true? Well, let me show you with an example. If I have a really simple example like 2, 5, and 8, okay, you can see that 2 is the first term, 5 is the second term, and 8 is the third term. So according to this formula, if I take the difference between T2 and T1, that's going to be 5 minus 2. And if it is equal to the difference between the third term and the second term, which is 5 minus 8, you can see that both sides of the equation are equal to each other, hence this is an AP. Okay, it makes a lot of sense. So that's our little example there. So now let's go ahead and apply this formula with some problems. So example 1, test whether the following is an arithmetic progression. So when you write down the formula, it's actually important the order. So it has to be the larger term minus the smaller term before it. So T2 minus T1 equals to T3 minus T2. So we're going to get T2 is -7, T1 is -12, but there's already a negative in the problem, so be careful. We're going to put it in brackets, so it's minus bracket -12, and this is going to be equal to -2 minus -7. So this becomes -7 plus 12 equals to -2 plus 7. On the left-hand side, that becomes +5. On the right-hand side, that is also +5. So therefore, since you get LHS equals to RHS, we can conclude that this is indeed an arithmetic progression. Wonderful. Very straightforward. So have a go at part B. All right, let's go through it together. So now if I plug in the same formula, T2 minus T1, we're going to get T2 minus T1 equals to T3 minus T2. Don't forget the brackets. This becomes -10 on the left-hand side. On the right-hand side, this becomes -12 plus 2, which also gives you -10 on either side. So therefore, we do get that the left-hand side is equal to the right-hand side. So therefore, this is also an arithmetic progression. Okay, now you can see just by looking at it, yeah, if you minus 10 from there, you get -2, and if you minus 10 again, you get -12. Very simple. We don't really need to do much working out. But if the question asks you to show that it is an arithmetic progression, you need to do this working out. You need to plug it into the formula. Example 2. Find the value of the pronumeral in each arithmetic sequence. So here we're actually going to be applying the same formula, but we're going to be using it to find unknown terms in our sequence. But we know for a fact that it is an AP, so therefore we can say that this is true. We know that it is an AP, so we know that the difference between these terms and the difference between these terms are going to be equal to each other. If they didn't specify that it was an arithmetic sequence, we couldn't assume that. So I'm going to say, write down my formula. T2 minus T1 equals T3 minus T2. We get x minus 1 minus 32 equals to 50 minus x minus 1. Notice how I'm always putting it in brackets if there is a negative, because we want to make sure that we're taking the negative of everything there. So this becomes x minus 33 equals to 50 minus x plus 1. And if you continue just to collect the like terms, this becomes 51 minus x there. Now I'm going to bring all the x's over to the left. So we get x plus x is 2x. If I add 33, we're going to get 84, or we get x equals to 42. Okay, now do a little check, see if that's true. If you substitute this into here, we get this will be 42 minus 1 is 41. So the difference between 32 and 41 is 9. If you add 9 again, you get 50. So that makes sense. Okay, great. Now we're going to do the same thing for this next 3 terms when we're looking for the pronumeral p. Now we know that it is an AP, so I can plug it into this formula. T2 is 3p plus 1, T1 is 2p minus 3, make sure it's in brackets, and then we get 5p plus 2 is T3, and then T2 is 3p plus 1. Okay, so now we just need to expand this out. Okay, and if we want to collect the like terms on the left-hand side we're going to get is 3p minus 2p, that just gives us p. And then we collect the like terms with the 1 and the 3, we just get p plus 4. On the right-hand side, we get 5p minus 3p gives you 2p. And then if we collect the numbers, we get 2 minus 3 gives you negative 1. So now if I bring them all over together, I'm going to bring the 2p, I'm going to bring it to the left. So we get minus p plus 4 equals to negative 1. I'm going to minus the 4, we get minus p equals to negative 5, or p equals to 5. Okay, now let's check if this is true. I'm going to check by plugging it in. So 2p minus 3 is 2 times 10 minus 3 is 7. 3 times 5 is 15. 15 plus 1 is 16. And then 5 times 5 is 25. 25 plus 2 is 27. So you can see that the difference between each of these numbers is a difference of 9. So it does check out. Okay, so that there is how you apply the above formula. That's basically the only sort of question that would require you to use this formula. Now, this is also the only one not on the reference sheet, but I would say that this is the most intuitive formula because you just need to find the difference between each of the 3 terms. Yeah, they have to be equal. Okay, now the next formula we're going to explore is the nth term of an arithmetic sequence formula. So we get Tn equals to a plus n minus 1d, where a is the first term, n is the term number. So if I'm looking for the 4th term, then n is equal to 4. If I'm looking for the 50th term, n is equal to 50, and d is the common difference. So there are many types of problems that you can get using this formula, and we're going to explore each type of specific problem so you can tackle any exam question. So example 3 says find the 15th term of the sequence. So if I'm looking for the 15th term, I'm essentially looking for T15. And let's write down what we know. So we know that the first term A is 6. We know that the common difference is 10. We're adding 10 every time. And we're looking for the 15th term that corresponds to n is equal to 15. So if we plug it into our nth term formula, Tn equals to a plus n minus 1d. Okay. I should also mention that the purpose of using this formula is, let's say you have some sort of sequence. Let's say the sequence is, let's say 2, 5, 8, comma, comma, comma. And we can see that they've given us the first 3 terms, but what if I wanted to write out the sequence for a very long time and I wanted to figure out what was the 152nd term? So what is T152? It would be extremely tedious to have to keep going and adding 3 every single time and then counting it up until you reach the 152nd term. So that's why plugging all this information into this Tn formula is going to make it much more simple for us. Okay, much less work. So we get Tn is the 15th term, A is 6, N is 15, so 15 minus 1, and our common difference is D. So we get that the 15th term is 146. Lovely, so we don't have to keep adding 10 every time to get that. All right, B, find the formula for the nth term of the sequence, negative 14, negative 18.5, negative 23. So in this question, we're not looking for a specific term. We're not looking for like the 50th term or the 10th term. We're finding a formula for the nth term. So whenever they ask for the nth term, it means we're essentially just looking for Tn. So we're looking for Tn, given that A is negative 14. Now what's the common difference? Okay, you can see that it differs by 4.5, and it's decreasing, so it's going to be negative 4.5. And we're looking for the nth term, so that means that we're essentially substituting n is equal to n. Okay, that sounds a bit odd, but that is what we're doing. We're keeping it in terms of n. We're not plugging in a value for n. So if we substitute that into the Tn equals to the a plus n minus 1d formula, we get Tn equals to negative 14 plus n minus 1 times negative 4.5. Okay, and then now I'm just going to expand this and simplify. If I expand this, we get negative 4.5n. Expand it, we get positive 4.5. And then if we collect the like terms, negative 14 plus 4.5 gives you negative 9.5 minus 4.5n. Okay, and that is our nth term. You're not going to just end up with a number. It's going to be an expression or a formula in terms of n. Now, the big benefit to finding the nth term is like if, let's say hypothetically, you have a question where it asks you to find the 10th term, the 15th term, the 20th term, the 100th term in the same question. So then what you can do is instead of having to plug it into the original formula every single time, you find the nth term formula and then you just plug in the n value. So if I'm looking for the 10th term, n is equal to 10. If I'm looking for the 15th term, n is equal to 15. If I'm looking for the 100th term, n is equal to 100. And then you get the idea. It's just easier that way. Okay, next, part C. Find the number of terms in the following sequence: 2, 5, 8, 1982, or 1982. So if I'm looking for the number of terms in this total sequence, you can see here, if I rewrite this, in this sequence, I can see that the first term is 2, the second term is 5, the third term is 8, but this term, I have no idea what n value this corresponds to. I'm just going to generalize it and say that this is the nth term, or this is Tn, and my job is to find the value of n that this corresponds to. This might be the 100th term, it might be the 200th term, we don't know. So our job is to look for the n value that corresponds to the term of 1982, given that a is 2 and the common difference is 3. So we're still going to plug it into the same nth term formula, but we're just going to have to just rearrange it to make n the subject. So the term itself is 1982, our first term is 2, n is n minus 1, and our difference is 3. So now if we expand this, we get 2 plus 3n minus 3, or we get 3n minus 1. So if I add 1, okay, divided by 3, we get 661. Now that might seem very large, but honestly, think about it. We started with 2 and we ended up at this number. The difference isn't that large. It kind of makes sense for it to be quite a big number. So we can also just always double check if this is correct. It's a good habit to develop early on when you're doing your homework, so that when you do the exam, you can actually check if your answer is correct. So if I sub in 661 into the original Tn formula here, so we know that a is 2, n is 661, minus 1 times the difference of 3. If you get this as your answer, which it is, it means you're correct. Next, D. Does 0 belong as a term in the following sequence? So let's write down this sequence. Now, our job is to figure out, is 0 actually a term in the sequence? Or does it perhaps go to 1 and then go down to negative 2 and then it doesn't actually have 0 as a sequence? Now, the way that you determine if 0 is a sequence or not, so let's say hypothetically, in a dream world where it is 0, what that means is, if I write that this is the first term, second term, and third term, it means that this 0 is going to correspond to an n value that has to be a whole number. So it either it has to be like the 10th term, the 12th term. It cannot be the 13.42 term ... That means that it's not going to work. It has to be a whole number value. So what we're going to do is we're going to let Tn equal to 0, And we're going to see what the value of n is that corresponds to that, and hoping that it is a whole number, an integer. And we're still going to use the fact that a is equal to 48 and the difference is -3. So if we plug it in, Tn equals to a plus n minus 1d, we get 0 equals to 48 plus n minus 1 times -3. 0 equals to 48 minus 3n plus 3. 0 equals to 51 minus 3n. 3n equals to 51 equals to 17. Beautiful. So the fact that we did indeed end up with a whole number term for n, it means that 0 is a term in the sequence. Next question, E. Find the first positive term of the sequence -97, -94, -91. So in this sequence, let's list it out. We're trying to find the first positive term because you can see here that although these are negative numbers, the numbers are actually becoming closer and closer towards 0 and the positive values getting larger and larger. So we're adding 3 every time. Eventually, if the sequence continues enough, you're going to end up reaching the positive values. So we're trying to figure out when or what is the first positive term and what is the n value that corresponds to that. The first positive term might be 1, it might be 2, it might be 3, who knows? We're going to figure it out. So what I'm going to do is I'm going to figure out what is the n value that corresponds to the Tn or the term itself being positive. And in order to be positive, I don't just say equals to 0, it means it's greater than 0. I'm going to let a equal to -97 and the difference is going to be a positive 3. So if we plug it into the Tn formula, we get this. We're going to get Tn equals to a -97 plus n minus 1 times d. And I'm just going to expand and simplify this. So -97 plus 3n minus 3 or -100 plus 3n. Now this is an expression for the nth term of my sequence. Now I'm trying to figure out when is the term first going to be positive. So I'm actually going to let the expression I have for the term, which is -100 plus 3n, I'm going to let that be greater than 0. So we get -100 plus 3n is greater than 0. And then I'm going to solve for n to see what is the first value of n, which makes that true. So we get 3n is greater than 100, or n is greater than 100 on 3, which is going to be 33.3. Now, you need to follow the direction of the inequality. That's why it's also important that the arrow is correct. If my arrow was pointing this way, I would actually have a different answer if it was pointing that way. Now, in this case, if you want to find what is the first integer, what is the first whole number, where it is greater than 33.3, then it has to be 34. So we just say when n equals to 34. Okay, that is when we have our first positive term. But you also want to pay attention to the wording of the problem. It says find the first positive term. So I'm also going to find out what is T34. So T34 is going to be actually I can just plug it into here, this Tn expression. We get -100 plus 3 times 34. That's going to give us 2. So 2 is our first positive term, which corresponds to n is equal to 34. Example 4. In an arithmetic sequence, the 4th term is 29, the 10th term is 83. Find the first term and the common difference and hence find the 15th term. So let's list out what we have here. So we know that the 4th term is 29, so T4 equals to 29. And we know that the 10th term is 83. Find the first term, the common difference, and hence find the 15th term. Okay, so we're looking for 3 things over here, given these 2 we know to be true. Now, when you look at this type of wording or when you try to just understand what we're looking for and what we're given, can you tell which topic of maths we have to use to achieve this? Well, we have 2 unknowns. And whenever you have 2 unknowns, it doesn't matter which topic of math it's from, doesn't matter whether it's year 10, year 11, year 12, It is almost always going to be simultaneous equations. Yes. So when you have simultaneous equations, you need to construct two equations which have two pronumerals which you're going to end up solving for. And the way that we obtain those two equations is we're going to use the two bits of information they've given us in the beginning, which is that the fourth term is 29 and the 10th term is 83. And we're plugging each of them into the Tn formula. The Tn equals to a plus n minus 1d. Okay, so if I substitute in T4 equals to 29 into here, we're looking for A and D. So those are going to be unknown. 29 is the term itself, so that's going to be in the Tn portion. A is unknown. The n value is what is the number that corresponds to that term. It's like if T4 equals to 29, it kind of means that I have like first term, second term, third term, and then the fourth term is 29. So n is going to be equal to 4 in that case. 4 minus 1 times d. So we get 29 equals to a plus 3d, and that is going to be our first equation. Now I'm going to do the same thing, substituting in that the 10th term is 83 into here. The term itself is 83, so we're going to get 83 equals to, a is unknown, n is 10, so we get 10 minus 1 times d, or 83 equals to a plus 9d. Okay, so these two here are going to be your two simultaneous equations. Now, if I wanted to solve this simultaneously, the easiest method I can think is the elimination method, because you can see that they're like toppling on each other, kind of like algorithm. You got the a's together, the d's together, and the constants together. And they also both have a singular a value. So if you just minus them, great, the a's cancel out. I'm just going to be a bit strategic here. I'm going to do equation number 2 minus equation number 1, just because I want to keep it positive. So 83 minus 29 is going to be 54. A minus a goes to 0, and then 9d minus 3d is 60. And then divided by 6, you get d is equal to 9. So that is your common difference. And then now I want to find out the value of a, so I'm going to substitute d is equal to 9 into equation number 1. We get 29 equals to a plus 3 times 9. 29 equals to a plus 27, or a is equal to 2. Now we can't forget our big picture goal as well. So the question says find the first term and the common difference, and hence find the 15th term. So now I'm looking for T15. A is 2, n is 15, so 15 minus 1 times a common difference of 9. That's going to give us 128. Okay, so that there is all of your little bits and bobs to completely answer this question.